Hello everyone, this is Engineer Salase from Hello Academy and Pen Boosters, and today we are going to discuss about proportional share. This is our chapter 9, and as you can see the book is operating system 3 pieces, so let's get into it. So in this chapter we are going to discuss about the proportional share scheduler. So fair share scheduler. This scheduler guarantees that each process obtains a certain percentage of CPU time, not optimized for turnaround or response time, like round robin or first come, first serve, or first job first schedulers. Where this scheduler is not concerned about turnaround or response time. The main idea of this fair share scheduler is about the fairness of the process. This scheduler more tries to address the issue of fairness rather than turnaround or response time. So the basic concept, how do we implement this fair share scheduling? And the answer is to hold a lottery through tickets. These are the main idea. So what is ticket? For example, ticket. This represents the share of a resource that a process should receive. The more ticket you have, the more chance of winning will be the probability. So the percent of ticket represents each share of the system resource in question. What I'm saying is, for example, there are two processes, for example, process A and process B. So process A has 75 tickets, means it receives 75% of the CPU. And if process B has 25 tickets, this means it receives 25% of the CPU. So the trick behind the ticket concept is should be addressed like this. So how this lottery scheduling work? What is the secret behind? That is the next question. So what we are going to do, the lottery peak should held every time slice at the time quantum of our CPU as per our operating system. The lottery peak will happen every time slice. Then what happens? The scheduler picks a winning ticket randomly. Okay, it's this system is randomized, so it loads the state of that winning process and runs it. So after every time slice there will be a schedule to pick the winning ticket. So as you can see, every time slice the scheduler performs a lottery pick and the process with that ticket number will run in the CPU. Then this process continues until all the process completed their execute. Let's see the example here. Let's say there are 100 tickets and process A has 75 tickets, let's say from 0 up to 74, and process B has 25 tickets, let's say 75 up to 99. Then every time with the scheduler the process happens, then let's see, scheduler wins ticket. The first time it runs, it picks 63. 63 is in the process A because process A is from 0 up to 74. So A will run until its time slice. Then the second time it will run again 85. 85 is B, then 70, then 39. Then it will keep on like this until all the process are completed. So the longer those two jobs complete, the more likely they are to achieve the desired percentage, because the more they run until the process completes, then we will pick in such a way. So that's how the lottery process works. So why we use randomness? As you can see, this system is using random. So the advantage of randoms are: number one, random avoids strange corner case behaviors. Second, random is lightweight, we only need to know few information such as the ticket number of the process to perform this task. Per process, accenting is reduced, and in third, randomness is very fast. Generating a random number from a generator is typically fast, so hardware supported as well. So in this, I just provided only 3 advantages, but there might be also another advantage. But these critical advantages are expressed in the textbook, and I advise you also to go and revisit the note. But these are some of the advantages of random. That's why the lottery scheduling system uses randomness. The other issue in lottery scheduling, how tickets mechanism works. The first one is, the first mechanism or the first concept is the so-called ticket currency. So this is the other concept we have to consider. A user allocates tickets among their own processes in whether currency is the headline, for example, local currency. We call it local currency. The system converts the currency into the correct global currency. The main idea here is what is local currency and what is global currency. For example, let's take an example here. Let's say there are 200 tickets. These are in the global currency. So process A has, let's say, 100 tickets and process B has 100 tickets. This is based on the global currencies, both processes. Now, user A has 2 processes, let's say A1 and A2 under A, and gives them 500 to each out of its 1000 in users A's own local currency. As you can see, the process A has 100 tickets only in the global currency. That is, it's giving now 500 to each because it has 1000 in its local currency. Again, user B has only one process B1 and gives 10 out of 10 total B's own local currency. So it should be, the system should change this local currency into global currency. So what it does is user A 500 A's currency to 50 global currency because we have 100 tickets in global currency of in process A. Again, 500 A's in A2 will be changed into 50 global currencies because 1000 is in local currency and 100 is in global currency. User B, the same thing happens, 100 B's currency, that means we have in global currency 100 tickets, so B is going to take 100. This is as simple as that. So the main idea here is local currency and global currency. This is the first mechanism which lottery scheduling use. The second mechanism is ticket transfer. What is ticket transfer? A process can temporarily hand off its ticket to another process. Useful in client-server application with server doing tasks on behalf of the client. In this kind of situation, the mechanism ticket transfer is used. The third mechanism, ticket inflation. This is a process can temporarily raise or lower the number of tickets, its own tickets as per its needs. If any one process needs more CPU time, it can boost its ticket. Assume that a group of processes trust each other to prevent abuse. This is the third mechanism. Now, how do we implement this lottery scheduling with C code? So in this simple code, as you can see, there are 3 processes. Let's assume we have A, B, C. Again, there are 400 global currency tickets in total. So current draw returns a ticket number of winning 300. Now, when the draw happens, the winning ticket which was drawn was 300. So what we are going to do, the first step what we are going to do is keep the process in the list or run or ready queue. Okay, here as you can see we have head here, then job A, job B and job C. So probably the most amazing thing about lottery scheduling is the simplicity of its implementation. All you need is, number one, a good random number generator to pick the winning ticket. In our case, we have 300 here. A data structure to track the process of the system. For example, we are using here linked list. And the total number of tickets. As you can see, we have total number of tickets, 400. To make a scheduling decision, we first have to pick a random number, the winner from a total number of tickets, 400. So what we are going to do now, let's say we pick the number 300. So the draw was already performed and 300 was already the winning ticket. So how is this process going to be done? Then we simply traverse the list with a simple counter, okay? With a simple counter used to help us find the winner. So if the winner is 300, how we are going to pick the number? So we are going to traverse through the list. So what we are going to do, the code walk the list of the process. This is our code. If you see the code, the counter used to track if we have found the winner yet. So we have integer, we have counter. Now the counter is set to 0 in the first place. So the winner use some call to random number to generator, again to get a value between 0 and the total number of the ticket. So as you can see, we have int winner get random. We have 2, 0 and total tickets. Again, the second current, use this to walk through the list of jobs. So we have the node T and current, we have head here. So loop until the sum of the ticket value is greater than the winner. So we have the while loop here, while current. So we have a counter here. So the counter, what the counter does, the counter plus the current, it will check to the ticket number. So if the counter greater than the winner number, then break. The program is doing like that. It will break, found the winner. Otherwise, what it does is the current, again the current will go and check to the next program. So what we are going to do, let's follow here. With our example of the winning ticket being 300, the following takes place. First counter is incremented to 100 to account for A's ticket, because 100 is less than 700. The loop continues. So what we are going to do first, let's assume A is there. So let's put the counter 100. Okay. Then first counter is incremented to 100 to account for A's ticket, because 100 is less than 300. The loop continues. Then counter would be updated to 150, because 100 is not greater than 300. The winning is 300, we already know. So at this position, what it does, the counter will go to next and it will add to the next process. Okay, so we're gonna take 50, the ticket number 50, so it will become 150. Then the counter would update to 150 ticket, still less than 300. When we check the winning ticket, again it is less than 300. So what it does, finally counter is updated to 400, because 150 plus 250 is 400. So clearly greater than 300 at this point, because the counter is 150 plus 250. So when it checks the ticket number, now it is greater than the winning number 300. So at this, what we are going to do, the code will break. Okay, the code will be break, and thus we break out the loop with a counter pointer at C. To make this process most efficient, that means the winning is C. Now C will take the CPU and it will run. So this simple code is the application of lottery scheduling. To make this process most efficient, it might generally be best to organize the list in sorted order from the highest number of tickets to the lowest. The order does not affect the correctness of the algorithm. However, it does ensure in general that the fewest number of list iterations are taken, especially if there are a few processes that process most of the tickets. I hope you understand this code, how it does the lottery scheduling, and you can go through the textbook as well. So simply it will check the counter and it will add the current. So the counter was set 0 at first, then plus 100, then it will check to the ticket, it is less than 300, then again it will go to next, then it will add to the ticket number, job B, again it will check it, 150, less than the winning code, so it will again not break. Again it will go to job C, 250 plus 150, it will become 400, now it is clearly greater than 300, then the program will break. That is how it does. So the next issue, how do we evaluate the performance of lottery scheduling? This is very important. So what we do is we first define U. U is unfairness matrix. The time first process complete divided by the time that the second process completes. This is very simple unfairness matrix. Let's see it in example. There are two processes, for example. Each process has a runtime of R10. The completion time of two jobs competing against one another, each with the same number of tickets. Let's say we have 100 and same runtime. So R, which will vary basically. Let's say first process finish at the time of 10, second process finish at a time of 20. So the unfairness matrix will be 10 over 20. This is 0.5. 0.5 means you will be close to 1 when both jobs finish at nearly the same time. Then we say perfect fair scheduler. But at this point, as you can see, it is 0.5. It's not perfect because we say it is perfect if the two processes are finished at the same time. That means if this product, the result one, then we can say the process was runs fairness. So there is a research was done. We will see it in the next slide. As you can see, lottery fairness study was done, and there are two processes and a simulation was conducted. What they did was in this simulation, two processes with runtime of job lengths are ranging from 1 to 1000. Over 30 trials was conducted. So as you can see, the job length is from 1 to 1000. So the x-axis shows job length and the y-axis shows unfairness average. And each job has the same number of tickets. 100 was assigned. What happens was, as you can see, if the job length is smaller, then the unfairness was very bad. So you will be close to 1 when both jobs finish at nearly the same time. Then we say perfect fair scheduler. So when the job length is not very long, average unfairness can be quite severe. As you can see, the process quite severe. So the job length, when the job length goes up to 1000, as you can see, the result become 1. Then we can say it is in the perfect fair scheduling location. So this is a simple study, but it will show you what is a perfect fair scheduler. So how do we assign ticket to a process? Now the main question is, one approach is to assume that user knows best, thus let users assign ticket. But the main problem is still it is an open problem in the lottery scheduling. This is a huge problem because how we assign the lottery? Until now we are theoretically assigning this ticket for this process and this amount of ticket for this process. But in a real scenario, we don't know how to assign ticket to a process. Okay, now let's continue to the second type of scheduler. This is the second scheduling, what we call it stride scheduling. In our first lottery approach, we used randomness or probabilistic approach. And basically will not deliver good result, especially for process with short runtime, as we have seen now in the simulation. So his striding scheduling uses a deterministic share scheduler invented by Waldspurg, and a stride of each process. How to determine the stride of each process? A large number divided by the number of tickets of the process. This is a formula. A large number divided by ticket number. Let's see an example. Let's take a large number of 10,000, and let's say process A has 100 tickets. So stride of A is 10,000 divided by 100, it will become 100. And process B has 50 tickets. Then stride of B is 10,000 divided by 50, it will give us 200. So this is how we're gonna determine the stride of each process. So a process runs increment a counter. Then a pass value for it, okay? Increment a counter, a pass value for it by its stride. So a pass value will be assigned to a process by its stride. Initially, it is 0, hence the algorithm will pick a process with the lowest pass value. So pick the process to run that has the lowest pass value. So the pseudocode implementation, as you can see, current is equal to remove main in the queue. This will, what it does, this program, what it does, pick client with the minimum pass. This is the first line of code. What it does is it picks client with a minimum pass. The second one, schedule current. What it does is the second line of code uses resource for the quantum. The third line of code, current pass plus current and stride, this compute next pass using the stride, because we are going to add the stride value into the current pass to get the new pass value. And the fourth line of code, this insert Q into the current. So what it does, it will insert the current value of the stride into the queue, put back into the queue. So let's see an example. Okay, stride scheduler example. So we have pass A, we have pass B, and we have pass C. And which process is going to run in the CPU now? Let's use the stride scheduler. As you can see, stride of A, let's assume now 100, stride of B to 200, stride of C is 40. So in the first run, as per the first line of code, what does it say? The first line of code, pick client with minimum pass. But as you can see in our first, all are 0. So since all the pass value are 0 initially, let us choose an arbitrary process. In our case, let's say A. Now A is running. So after some time, when A is completed, the pass time of A will be updated by the stride of A. So as you can see, we have 100 here. So let's show you here. The second, you see current, the resource for the quantum, and complete next pass using the stride. So as you can see, this one is updated by the stride of A. Now, in the second line of code, in the second process, A is already completed. Now, again, both is 0, so let's say we pick B. So B is running in the CPU now. So after some time, in the time quantum, B is completed. So what we are going to do is, in the third line, the pass of B will be updated by the stride of B, 200. Now, the least pass time is only C, because it is 0. C will continue now. C will run, then when it's finished, now it will be updated. So the path of the C will be updated by the stride of C, it will be 40. Now as you can see from here, which one is the least path? C is the least path, so C will run. After some time C will finish. So C will be updated, 40 plus 40, it will become 80. Okay, it will become 80. Again from 100 to 180, C is the least again. So C will run and it will update the stride by 40, 120. At this stage, 120, 200 and 100, A will be took over the CPU and it will run for the time counter. So A will run. So after that, in this stage, A will update its pass time by the stride 100, it will become 200. Again, in this stage, which one has the pass is the least pass, C will have the least pass. So C will take 120 and it will run for the time quantum and it will add the stride of 40 and it will become 160. And at this stage, again C will run, then 200, 200, 200. So this process will continue until the processor completed their execution line of code. So in this way, the stride scheduler works. But what is the problem? If new job enters with pass value of 0 at any location, it will monopolize the CPU. This is the big problem, because if the least pass number will take over the CPU and run. So if any process comes with 0 pass time, then it will took over the monopolize the CPU and all other process will be idle. That means starvation. So lottery is still better since there is no global state to be maintained per process. In this case, there is override for each step of record the state of the process. What this statement says is, for example, process A is running here, then process B comes. So there is a lot of context switch here. What does this mean? From A to B, when B took over the CPU, the progress of the process A should be registered in the cache and in the register in the kernel of the operating system. So again, when it loads, the progress of the register should be loaded into the RAM to continue from where the process was stored. So in this case, as you can see, the context switch of the process, every time the progress should be registered in the RAM, in the register, in the kernel of the operating system. Again, when the process comes, again, it should load all the data, the progress of the data into the RAM again, in the read-access memory, and the registers, and in the kernel. So in this way, there is too much context switch between the process. Then this will cause the overhead in our system. But in the lottery system, this doesn't happen. So that is the drawbacks of the stride scheduler. So in summary, we have introduced the concept of proportional share scheduling and briefly discussed two implementations, the lottery and the stride scheduling. Lottery uses randomness in the clever way to achieve proportional share. Stride does so deterministically, as we have seen. Although both are conceptually interesting, they have not achieved widespread adoption as CPU scheduler for a variety of reasons. The first one is such approach do not particularly mesh well with input-output. Another is that they leave open the hard problem of ticket assignment. How do you know how many tickets your browser should be allocated? General purpose schedulers such as the multi-level feedback queue we discussed previously, and other similar Linux schedulers do so more gracefully and thus are more widely developed. As a result, share schedulers are more useful in domains where some of these problems, such as assignment of share, are relatively easy to solve. For example, in virtualized data center, where you might look at to assign 1/4 of your CPU cycle to the Windows virtual machine and the rest to your basic Linux installation. Proportional share can be simple and efficient. See words further for further detail on how such a scheme is used to proportionally share memory in virtual machine, VMware's ASX servers. So in general, this is the other type of scheduling. So we focused on the rotary and stride scheduling system. And in short, this is the chapter 8 of the book. So all the resources, the data, notes, everything is taken from the textbook of Andrea and Remzi. And that was it for today. Thank you so much. I really appreciate it. And next time I will come up with chapter 10 of the book. And this is Engineer Selassie from Yale Academy Boosters. Bye bye. Thank you.